Hi everyone. From this video, I am going to start a new subject, that is switching theory and logic design. Switching theory and logic design generally falls in second year of BTech for either triple E or ECE students. Okay, most commonly ECE students are having the subject, and the subject is very easy to understand but difficult to pass sometimes. Okay, because it is completely the subject is dealing with only zeros and ones. But as we are going further, flip-flops, registers, counters, such type of devices will come. But those topics are FSM will come, finite state machines. Those topics are somewhat difficult to understand and as well as to present in the examination. But if you clearly go through it, definitely it will be very easy. Okay, I will deal each and everything very clearly in the coming videos. So first, what do you mean by switching theory and logic design? Before going to the entire subject, first let me explain what do you mean by switching. Switching is nothing but there are two options. It may be either off or on. Off switch and on switch. Off switch is nothing but in our terminology here in the electronic terminology we are saying off switch is nothing but we are saying it is 0. On switch is nothing but it is 1. If you see any electronic device, it is having a switch like a printer, scanner, we are having switch. That switch is given with either 1 and 0. Okay, switch is given like this. It is 1 and it is 0. When you press here, then 1 means it is on. When you press here, 0 means it is off. Okay, that is the meaning of this 1 and 0. So generally switching off, nothing but we are giving 0 here. Switching on means we are giving 1. Okay, that is the logic 0 and logic 1. In generally we call this 0 as logic 0. Logic 0 and 1 as logic 1. Logic 1. That means there are two logic levels for any switching device. There are two logic levels as logic 0 and logic 1. Logic 0 means off state. Logic 1 means on state. Okay, 1 is always representing the on state, upper level, and 0 is always representing the bottom level, nothing but off state. So if you take the waveform in terms of waveform also you can represent this logic levels like this. 1, 0, 1, and again we are having 0 here. Suppose in the next instant also we are having 0 and it is 1. That is the representation of any logic function and the waveform. Okay, this is the meaning of switching. Switching theory, that means we are going to study completely about ones and zeros. What are the different numbers we are having to represent these ones and zeros? That means the decimal numbers can be represented in the form of ones and zeros. So that is completely we are going to study in the switching theory. And logic design. Logic design is nothing but we are performing the operation between ones and zeros by using some logical gates, AND gate, OR gate, NOT gate, and exclusive gates XOR and XNOR, and universal gates NAND gate and NOR gate. So all these gates we are going to study with respect to the implementations of like flip-flops, registers, counters, and so on. That is about logic design. We are going to design logical circuits using the standard basic logic gates. Okay, this is about switching theory and logic design. So in the logic design, we focus on designing circuits using gates. Designing circuits using gates. Nothing but gates are nothing but basic gates, or it may be universal gates, or it may be exclusive gates. Okay, so basic gates are nothing but AND gate, OR gate, NOT gate, and universal gates are nothing but XOR and NOR gate and NAND gate, and exclusive gates are nothing but XOR and XNOR. Okay, these are the different gates we are going to implement the logic circuits using this logic gating circuits. That's why it is known as logic design. Okay, this is about the introduction of this switching theory and logic design. Now, number system. Number system. What do you mean by number system? In number system, we are representing a number by its corresponding binary information. A decimal number, or we can say it is an integer. Decimal number is nothing but it is an integer, 1, 2, 3, 4, so 5 and so on. Okay, that particular decimal number is going to be represented in its equivalent binary information, binary digits. Okay, suppose I am taking 1 is represented as 0 first. 0 is represented as 0. So suppose if it is a 2-bit of information, then it is 0 0. 1 is represented as 0 1. 2 is represented as 1 0. 3 is represented as 1 1. That means binary is nothing but we are representing the input integer number or a decimal number in terms of its equivalent 2 power digit numbers. So 2 power here, see, this is 0th location and this is first location. That means it is 2 power 0, 2 power 0th location, and it is 2 power 1 location. This particular value multiplied by this 2 power 0 plus this particular value multiplied by 2 power 1. That is the meaning of binary information. Suppose how I have taken 1 is nothing but in 0th place, units place, we are having 0. So 0 into 2 power 0 plus 0 into 2 power 1. This is the representation. So if you simplify this, this is 0, this is 0, so 0. Sorry, this is for 0. First number 0. Okay, this one is completed. And now coming to the second number, 0 into 2 power 1, and in the units place we are having 1 into 2 power 0. That is equal to 2 power 0 is 1, anything power 0 is 1, so 1 into 1 1, and this is 0, so output is 1. And similarly 2 is represented as 1 into 2 power 1 plus 0 into 2 power 0. This is 1 but multiplied with 0, so it is 0, and 2 power 1 is 2, 2 into 1 2. And similarly 3 is represented as 1 into 2 power 1 plus 1 into 2 power 0, that is equal to, this is 1 plus this is 2, that is equal to 3. In this way we are getting the binary information. That means the binary digits can be represented by 2 power 0, 2 power 1, 2 power 2 and so on. Okay, as here I have taken only 2 bits of information, 0 0. If it is 3 bits of information, then 0 0 0. If it is 4 bits of information, 0 0 0 0. Suppose for the same number 3, I want to represent in 4-digit format, 4-bit format, then it will be like this, 0 0 1 1. Okay, the front bits becomes 0. Front bits are becoming 0. Then it is 2 power 0, 2 power 1, 2 power 2 and 2 power 3. First 2 becomes 0 followed by next 2. Hope it is clear. So in number system, we are having decimal number, binary number, octal number, hexa number. Such type of numbers we are going to represent in terms of its equivalent numbers. Okay, in binary information, in binary data, we are taking 2 powers. In hexadecimal, we are taking 16 power. In octal number, we are taking 8 power. In whatever may be the number, that corresponding power will come. Okay, in decimal, if we are saying in decimal 10 power data, we have to take 10 power 0, 10 power 1 like that. Okay, so in general, In general, the value of any mixed decimal number is given by dn, dn minus 1, dn minus 2 and so on, d1, d0, d1, d0 dot d minus 1, d minus 2, d minus 3 and so on, d minus k. Okay, what is the meaning of this one? See here, until this decimal point on the left hand side we are having all the values which are related to the number, and on the right hand side we are having all these are decimal numbers, points. Okay, for example, the same number can be written as d power n into decimal means 10. It is decimal number. See, in the beginning only I told it is a mixed decimal number. Decimal number equivalent number can be represented in terms of 10 power. Okay, if it is a binary number we have to write in terms of 2 power. As it is a decimal number, it is 10 power n plus, that means its equivalent number we are going to write here, dn minus 1 into 10 power n minus 1 plus dn minus 2 into 10 power n minus 2 and so on, d naught into 10 power 0 dot d minus 1 into 10 power minus 1. So whatever the number is there in that point, in that place, that is multiplied by that 10 into that particular place position number, again plus d minus 2 into 10 power minus 2 and so on. Okay, now for example, consider a decimal number 9256.26, 9256.26. So how to represent this number? In the above format, that is equal to 9 is having in thousands place. So 9000 plus expansion of this number 200 plus 50 plus 6, 50 plus 6, that means 9 into 1000, 2 into 100, 5 into 10, and it is 6 into 1 plus 2 into, see here, 2 is after decimal, this 2 is there after decimal, that's why it is 1 by 10 as it is in the first place, plus 6 into 1 by 100 as it is in the second position. So we can write it as 10 power 3 plus 2 into 10 square plus 5 into 10, that means 10 power 1 plus 6 into 10 power 0 as we have done in the case of d number here. See, dn is nothing but now it is n is equal to 3 plus 2 into 10 power minus 1 plus 6 into 10 power minus 2. This is the way of representing a decimal number like this. So another example, you can take any example. Another example, 6592.69. How to write this one? 6 is at the which place? See, 0, 1, 2, 3. So 6 into 10 power 3 plus 0, 1, 2. 5 is at second place. So 10 power 2 plus 9 into 10 power 1 plus 2 into 10 power 0 plus 6 into 10 power minus 1 plus 9 into 10 power minus 2. This is the way of representing a given number into its decimal format. Decimal format. Okay. In the next video, I will tell about the nines and tens complement, how the nines and tens complement is going to be helping us in the calculation of subtractions and additions. Okay. Thank you.